This is the final video portion for the introductory class of Material Science and Engineering at Clemson University. Hello, my name is sdtate. Currently my major is Material Science and Engineering with an emphasis on polymers. However, I think I'll be switching to the emphasis on ceramics. A polymer is typically a plastic and resin. The molecular structure consists of a large number of the same units bonded together. A ceramic is an inorganic and non-metallic material. Common ceramics would consist of glass, pots, and toilets. The dream job of mine would be to help develop new technologies and apply them to the current world. For example, applying new materials to increase manufacturing productivity. This is essential in the modern world because it does not make companies start from scratch, but instead evolve to meet the current technological standards of society. Another thing that interests me are quantum mechanics. This is the future for the human race. Scientists could use this to determine the properties of materials and other aspects instantly. This technology is not yet ready, but will be ideal working with such an advanced technology. For the job of my future, it would be necessary for me to be able to use all aspects of a material science degree to fully understand the problem at hand. For example, I must be able to characterize materials to further establish the properties and behaviors. This is important because you need to know the ins and outs of each and every material in order to use them to their fullest. I must also be aware of the quality and breaking rates of the material at hand. In this chart, you can see many of the characteristics are proportional and inversely proportional to each other. For instance, hardness and density directly correlate to each other, while dimensional stability and thermal shock are inversely proportional. Knowing this information can really influence the outcome and the uses of the material. For example, one might need to know the ceramic density of the material. This can be beneficial to find the hardness and ductility, which in turn can heavily rely on the safety of an experiment or of the manufacturing process. I will show how to calculate the theoretical density of the FeO. I will also be finding the unit cell volume, which is very helpful in many other equations. First, I will explain what everything stands for in this equation. The rho is the theoretical density for the ceramic material we are calculating. In this case, will be the theoretical density of FeO. The N, with the apostrophe, is the number of formula units, all ions included in the chemical formula. The N sub A is Avogadro's number, which is the number of units per 1 mole. The V sub C is the unit cell volume. This can be calculated knowing the atomic radius of cations and anions. The sigma A sub C unit corresponds to the sum of the atomic weight of all cations in the formula unit, while the sigma sub A corresponds to the anions. To find the N apostrophe, one must count the total ions. For FeO there was 4, because the iron ion has a 2 plus charge and the oxygen has a 2 minus charge. So when you add up the two charges, there are 4 ions total, 2 for the cation, 2 for the anion. FeO is a rock salt. This crystal structure looks like this. V sub C is equal to A cubed. So we have to find what A equals. 1 full side of the structure is equal to A. 2 halves of the oxygen ion and 1 full iron ion make up A. Therefore, A is equal to the radius of the iron 2 ion multiplied by 2, and the radius of the oxygen 2 minus ion multiplied by 2. This table shows the ionic radiuses of the specific ions. Using the values given for Fe2 plus and O2 minus, we can calculate what A equals, and then subsequently what V sub C equals. The radius of the iron cation is 0.077 nanometers, while the radius of the oxygen anion is 0.14 nanometers. Multiply each of the radiuses by 2 and then add them together. V sub C equals 0.434 nanometers cubed. Therefore, the unit cell volume is 0.08175 nanometers cubed. However, the theoretical density will be in units of grams per centimeters cubed, so it is easier to convert the unit cell volume instead of the final result. So therefore, V sub C is equal to 8.175 times 10 to the negative 23rd centimeters cubed. Now only the sigma A sub C and sigma A sub A values are left before finding the theoretical density rho. Using the periodic table of the elements, we can find our last values. The atomic weight of iron is 55.845 grams per mole, and the atomic weight of oxygen is 15.999 grams per mole. These correspond to the sigma A sub C and the sigma A sub A values. Since everything needed to calculate the theoretical density of FeO is acquired, just plug in the numbers and do the math to find the theoretical density of rho of FeO is 5.837 grams per centimeter cubed. The density of a material can be used in several ways. Schucker and Gammon in 1970 were trying to relate the spectral scattering intensity to the density of states of vibration in amorphous materials. This is more complicated than this course entails, however it's very interesting to realize that the density of some materials can be changed with an influence. To learn more about thermal behaviors, theoretical densities, and much more, the chapter Physical and Thermal Behavior in the book Modern Ceramic Engineering is very engaging and will explain the different types of physical and thermal properties of materials. For keeping up to date with the current technologies in material and science and engineering field, the journal Advances in Material Science and Engineering is exceptional. This journal has thousands of entries to learn more about the new engaging technologies of materials.